This is part 7 in a series of videos in which I'm attempting to design a drop-in replacement for a Fluke 9010A cassette drive. And what I want to do is end up with a device that we can plug small discrete memory cards into. And the idea there is to duplicate the functionality of the cassette tapes without the complication of having to use actual tapes, and of course the cost associated with doing that. Unfortunately, the Fluke tapes are fairly rare and have become very expensive, and they're fairly fragile anyway. Also, they're quite slow, and there's no real need for the reads and writes to take so long. There is a serial option with Flukes that you can install, but it's a bit of a pain having to boot up the PC just to load some programs into it. It's much more convenient to use the tapes, and of course it'd be far more convenient to use the memory cards. So what I've done so far in the previous video, as we got as far as installing the basic input and output, that was the command in and the command out latches, and that worked. So I've tidied up the wiring for that, and now I've installed another latch, which is the data input latch, and that allows data to be transferred from the Fluke into the microprocessor that we're using. And there was a few complications getting the timing right, and I'm talking here about the bus timing rather than the firmware. But once I've done that, the next step was to try to emulate the operation of the cassette tape. Now, a quick read through the manual, there's very sparse information in here, so trying to figure out the protocol that's used, etc., was quite difficult. But a quick browse through the manual, and this is the only information I can really find. But it is quite useful. It does give us the bit values for the data byte that's used for the status of the cassette drive. So in other words, when the Fluke is trying to figure out what the state of the cassette drive is, it reads the status byte that's normally in the 8041 device on the cassette tape, and the firmware in the cassette drive keeps this byte maintained with information based on the current status of the tape drive. Now, of course, being a tape drive mechanical device, there's some fairly weird timing requirements, and also things that while we don't really need them, we have to cater to them because the Fluke expects certain things to happen. So for example, when it tries to access the tape, it expects the tape to rewind under the control of the device on the cassette drive, but then it expects the drive to report that it's rewound. That's all autonomous within the cassette drive, but the Fluke still expects the cassette drive to report successful completion of these steps. So I've been going through this, figuring out exactly how to get data to transfer to and from the Fluke, sorting out various timing requirements, and because the Fluke, when it wants to read the data, asserts the control lines, and then within a fraction of a microsecond it expects the data to appear on the data bus. This can't be done just purely in the firmware in the microcontroller. It has to be done through a series of input and output latches. So the left hand side of this assembly are the latches and a decoder. We need the decoder to make sure that the correct latch is updated depending on which particular control lines are in which particular state. Now, once I'd done that, I'd been going through the firmware and reverse engineering this, and once we take out all the encoding for the tape, the rewind functions, timer functions, we end up with a loop. It's quite a tight loop, and what it's really doing is it's setting various flags within the controller. Some of the flags in the status byte in the original chip are set automatically depending on which particular command is received. So we have to emulate that in our code, and what we then end up doing is toggling various flags at the right time to make the Fluke think it's talking to the cassette drive. And that's all done in a relatively small loop, and what it's doing here is it's setting a flag to tell the Fluke it's ready for the next byte. The Fluke is then, within a short time, coming back, writing the byte into the data input buffer of the device. There's no way of knowing exactly when it's done that, because it kind of depends on what else the Fluke is doing. So we need to have our system monitor the control lines to see when the data byte's available. And then we read the byte, and there's a function call down here that would normally take the byte that's been read and encode that onto the tape using fairly complex encoding. And then it jumps back to the start of the loop, and it keeps going until all the data is written. So the way that the tapes work on the Fluke is very simplistic in terms of transferring data to and from it. It doesn't maintain an index or anything like that. It's simply the entire contents of the memory are transferred into the tape, and then when you read the tape, the entire contents of the memory are updated from the tape. So you can't just select individual programs from the tape. It's an all or nothing thing. The tapes hold 12K of data, and so we'll be emulating that. There's no point going beyond that, because of course the Fluke would just flag an overflow if we try to put more data than that onto the system. And it also encodes and saves the actual configuration data, so it's not just the program data that's saved to tape, it's actually the configuration of the machine. We don't need to really be concerned about that. It's just really making sure that we save the entire data stream that's sent through to our device, and then we read that back in the right order to the Fluke when it's doing a read, and the Fluke will take care of where to put the individual data bytes. We just need to make sure they're correct. Okay, so I'll take this over, we'll get it onto the emulator system, and I'll just give a very quick run through the firmware to show how far I've got, and then in the next video we'll start looking at adding the read option. The Fluke and our device attached to the emulator system. Hopefully you can see it okay. It's tucked in the corner here next to one of the development PCs, and we're looking at the source code here, or at least the system I'm using to develop the source code for the PIC. And one thing I would say here is, using a design like this, it doesn't really matter which particular sort of microprocessor you use. It's kind of obfuscated behind the hardware interface, so as long as the code running on it runs the latches correctly and does the right things regarding handling the data and setting the flags, then pretty much any sort of processor with sufficient speed and power would work fine. So I'm running this through a serial emulator. What I'll do now is rebuild the code, and that will rebuild the code that's currently in the system and program it into the PIC ready to run. And what we're looking at here on the screen, I mean, the firmware is far from complete. This is just very rudimentary testing that I'm doing. So the way I have this configured, there's no memory device attached. I've just set up a small buffer within the PIC, and any data we read will be read into that buffer. And this panel here is showing the contents of that buffer. Any values that change are shown in red, and the reason they're all red at the moment is, of course, we haven't yet run the system, so none of them are defined. As soon as I start running this, what actually happens, a very quick run through the firmware as it stands. We have a table up here, a few characters used for the incoming and outgoing data. The status byte, which is maintained by the firmware in the same way that it would be within the 8041 in the original system. And then what we have is initialization blocks, so we make sure that all the ports are initialized the way that they should be. We then initialize all the values to make sure they are at the correct starting point. This is just to make sure that we don't interfere with the Fluke when it starts trying to access the system. This is normally done within a couple of microseconds of the system booting up and long before the reset on the Fluke is cleared. But even if this doesn't run, because of the way the hardware is arranged, it still shouldn't stop the Fluke from running. So in other words, even if our micro crashes, it shouldn't interfere with the Fluke. We then have the little block that sets the command out latch, and this is just to make sure that the latch that we're using for the command control is initialized properly, so the microcontroller doesn't start responding to a command that hasn't been received. At boot up time, we may just get noise on the bus from the Fluke, and we don't want our micro responding to that. Then just a small loop to clear the buffer table. This is not permanent, this is just for test purposes, but to make it clear, I'm just setting all the values to 0. And what we then do is we start a main loop, and this is where we start to emulate the loops in the firmware on the original system. The first block is to update the cassette status information, so this will be cassette present, write protected, this sort of thing, and it just updates the status byte. One thing you'll notice here is I'm getting several lines repeated, and the reason I've done that is because this micro is running at 48 megahertz and it's way faster than the devices can respond to. So by duplicating these lines, I'm effectively putting a small wait loop here, but I don't want to put an actual call to a wait function, that would take too long. Could use NOPS of course or anything like that, just something to replicate the line and slow things down. The reason I'm actually replicating this line is it gives me a bit more robustness in operation, because this is talking onto a shared bus that may have some capacitance. Microcontrollers like PICs can sometimes fail to set bits if they are heavily loaded, and by doing this I'm making absolutely certain that the value is set, as well as introducing a delay. Okay, other parts of the code incidentally can change the status byte. This is the flags I showed earlier, but this is where it's written to the status output buffer. We then look at the incoming control byte to see if there's any new command for us to process, and if there is, it's handled appropriately, whether it's a data byte coming in or a control byte coming in. Then it saves the value on the bus into the correct character. And then again, this is just for test purposes. Any incoming data that's detected is written into the buffer. Now before any of this will work, of course, we have to fool the Fluke into thinking it's talking to the tape drive. So nothing's happened at this point other than we've potentially set the status byte. But when the command is received from the Fluke, in this case we're starting with the write tape command, that's a value of 11 hex, and that's what this line is doing here. So we're handling all this in a switch. When we detect this value, then it goes through a series of events, and then ultimately it just runs back and forth through the latter stages of the switch, and this just causes the control lines to be toggled in the same way they would be in the original firmware, and that causes the Fluke to continuously send the contents of memory, and then the section higher up can read the incoming bytes as they are ready. You can't do it in a continuous loop, of course, because we don't have a handshaking system as such. There's no direct timing information as to when the data will be available, and that means that we have to use the status of the control lines as the flags to determine when data is available, and then we read the data, reset the flags, and go back into the loop and wait for the next byte to appear. Okay, so I'll start running this. Notice that nothing seems to have happened on the Fluke. Also I've got a trap set down here where the red dot is, so when we get down to this point the firmware will stop, and this is just at the point where it's read the full contents of the buffer in the PIC. Obviously there's far more data coming through than the PIC can handle internally, because we don't yet have an external memory fitted, I don't want to start overflowing the buffer, so it just stops when it's full. We'll still be able to see if there's incoming data, and I'll explain how that is in a few seconds. But the first thing to bear in mind here is this is now running. So if I effectively remove the cassette by taking up this link and then try to run the write tape command, you see we get a message saying no cassette. I'll put the link back in, and now we can run this function. So when I run this, what should happen is a bit of handshaking will be carried out, and the device will essentially go through the steps from the Fluke perspective as if though it was rewinding a tape. It's very quick. There's obviously no tape, so I can do this very quickly in just a few microseconds, but the Fluke will see it as a tape being rewound, hitting the clear leader at the end, and then driving off the tape into the position where it's ready to start writing data to the tape. It then starts toggling the control flags, waiting for the Fluke to start sending the actual data. So we'll continue and get this to start up. So you can see that I haven't got as far yet as setting the end of operation flag, so it just keeps running. But you can see that the firmware has stopped, and also we can see all the values are now red, so every single one has changed. And more importantly, we start off with an AA55, and I'm sure most people will recognise that's alternating bit patterns, and they're the first 2 bytes that the Fluke sends to synchronise the data stream. And then the rest of this is the data from memory. The first block down to probably about here is so the first 2/3 of what you can see here is configuration data. Now if we reset the micro, reset the Fluke, and then restart the micro and do the same thing again, now you can see that although we've stopped in the same place in the firmware, none of the values in the buffer have changed. They've all been rewritten, but because they're written with the same value, then none of them have been altered. And that's a good sign that we're doing this reliably and we're not encountering any errors. I did leave this running for an hour doing nothing but cycling this back and forth, and it didn't pick up any errors, so it does appear to be working properly. And looking down into the switch, you can see there are various delay values here that are used to these are not required for exact timing, but we need to keep something sensible in terms of the loop rate, and that's what they're there for. What we can do now is change one of the configuration settings. So if we go into the setup for the Fluke and we change something, and then we go back into the command that we just ran, so I'll restart the PIC and we'll rerun the write tape. Then you can see this value here is red, it says 6F, and the reason it's changed is because this is where the value in memory is stored for the setting that we just altered, and any value we change in configuration will show from about the 3rd byte down to just over halfway down this screen of the buffer. Beyond that, we have the pointers for the programs. So if I enter a program, so program 1 has been created, I'll enter a single command into that program, exit the program, and just out of interest, if we go back in and select the program, we can see it's 8 bytes long. So I'll come back out, we'll restart the PIC, rewrite the data, and now notice down here we're getting a value that says C0, and the C is a bit misleading. We'll come back to why it's saying C in a few seconds. What I'm going to do is just spend 30 seconds or so making a slightly bigger program, and then we'll come back, rerun the PIC, and we'll have a more detailed look at what's actually going on here with the data. Okay, I've entered a bit more information for program 1, restart the PIC, we'll download the data, and if we now look down here, we can see we have a value of 5A followed by a value of C0. So what I've done, I've entered more data for program 1, I've also entered program 2. If you work out what 5A is, this hex of course is in decimal, it's 90. If we now go and select program 1, we can see it's 90 bytes long. So what we have here is the size of the program. So these bytes are the placeholders for the size of individual programs, and C0 is the default minimal size for the program. Notice we have 5A, C0 and then nothing. If we enter program 3, so I'll create program 3. It's created, I'll put in one command, exit the program, and now we'll reread the memory contents. And notice now that we've gone from 5A C0 to 0 to 5A C0 62 C0. So in other words, these values here are the placeholders for information about the individual programs. And because they are being consistently read and they're in the right place, then we can be fairly certain that this mechanism is working. It's only streaming data, so if it's working for the first 200 bytes, then almost certainly it's working for the rest of the data. What I'll do now, of course, is create a bigger buffer and then just start making sure the entire contents have been reliably read, but it looks very promising so far. And if that's all working fine, all I have to do is put in the end of tape response bit. That's just setting the flag in the command, and then this will cause the Fluke to give a successful tape read. What happens then is the Fluke will try to rewind the tape, and then it rereads it and compares the value against the values that it's saved. So it's a two-step process, but the second step is just really an extension of the first. So if I can get it working through the first section, then the second part should work fine. Okay, so that's how far I've got at the moment. You can see that it is working fairly nicely, it's reliable, it gives consistent results, and it does look like it's going to be a fairly reliable way to actually save data on the Fluke, and it will obviously make quite a nice addition to anyone if they have one of these and they want a more convenient way to store data. Comments welcome. In the next video I'll be looking at completing the write function and then adding the read function.